Okay, I will continue with the second class, with the second main course, where I will discuss the symmetries of differential equations, the application of them. So in this presentation, I will discuss about the application of symmetries on PDEs and the reduction of dependent variables and the type 2 symmetries, and the application of symmetries in fluid dynamics. Then we'll discuss the application of symmetries in general relativity in gravitational physics, and how AI can assist us with the symmetry analysis. So we have, I will continue from where I was stopped the last time. The last time I talked about ODEs. So a partial differential equation is nothing else than a function in the Z space Bn, where now as C as the independent variable, X are the independent variables, and U are the dependent variables. A comma means partial derivative with respect to the dependent variable X, independent variable X. As in the case of ODEs, we define the variant of the PDE under the infinitesimal transformations with generator X with the following definition. We shall say that the generator X of the transformation 1 is called a lead point symmetry of the PDE if and only if there exists a function lambda such that the following condition to be true. This is exactly the same definition with the case of ODEs or with the case of functions. In the case of PDEs, the coefficients of the prolongation, the first coefficients of the prolongations are defined by the following formula, where the capital DI is the total derivative given by this expression. Now, in terms of the partial derivatives of the components, the first and second prolongation vectors are expressed like that. So this is the base manifold, this is the X, which is the generator of the transformation, and the extension of the generator of the transformation, the extended manifold, is given by these two expressions, the first one and the second prolongation. Now, for example, we can use these definitions to find the least symmetries of the 1 + 1 heat equation given by this formula, and let X to be the generator of the infinitesimal transformation, be this one. Then we shall call that this least symmetry if and only if the application of X gives on the differential equations reduced to that system, that equation which we have here. This eta XX and eta t are the two prolongations of the vector field, the two prolongations in the UT direction and the UXX direction, as given by this expression. It's important to mention, I didn't mention before, that I am assuming Einstein summation condition. So when I have two indices with the same form, up and down, I assume that I sum on these indices. Substituting eta and eta XX and collected terms of derivative of U, we find the following determining equation. So the solution of this system will provide us with the symmetries for the heat equation. We solve the system and we find the general solution to be of this form. Well, function we have here in these coefficients, we have, as you can see, 6 constants, A1, A2, A3, A4, A5, and A6, and a function B, where B is the solution of the heat equation. Now, each constant generates a symmetry vector. This 6 constants generates a basic of symmetry vectors, while Btx is a solution of the heat equation, and we know that the solution of a PDE is also the generator of a symmetry of PDE. That is actually, if you use a solution to transform a solution to another solution with a definition of a symmetry, then you will get the same solution, assuming that you apply the solution. So this symmetry, the Btx, it's with a solution of the heat equation. It is a trivial symmetry. It has no real application, but it can only give us the information that the equation is linear, the original equation that we studied. So the generic vector field is this one. Now, how we can use and we apply this vector field to understand and how to apply the symmetry vectors in the analysis of PDEs. Function, we have a definition that the function is an invariant solution corresponding to the differential generator x if and only if ux is an invariant of the differential generator xu equals 0 and solves the PDE. Solutions are transformed into solutions. Assume a PDE which admits a Lie point symmetry and let U be a solution which is not invariant under the Lie symmetry. Then under the transformation with generator X, the solution defines a family of solutions of the PDE. This is a theory. So, for instance, the point transformation which corresponds to the Lie point symmetry, this one, of the heat equations, the transformation is this. This is a point transformation generated by the differential transformation, and this is nothing else than a solution where U bar. If U is a solution, then U bar is also a solution for the differential equation. And you see is okay. This is a way to construct one solution from another. So if this is a solution, then by applying the transformation in the solution, we ended to this form, then we were able to construct a new solution for the differential equation. Now, so far, we have considered point transformation which depend on the variables of the base manifold only. However, there exist transformations who are defined in the Z space and depend also on the derivatives. The infinitesimal transformation, which is defined in the Z space, whereas you can see function xi and eta that depends on the derivative, are called as Lie-Backlund transformation. This point transformation does not concern the present work, but this study, but we present it for the completeness and the basic definition. So the generator, which is the generator of Lie-Backlund transformation for the differential equation, this one, H, is a symmetry if and only if there exists a function lambda such the following condition to be true. As you can see, there is no any change between the definition of the Lie symmetry condition with the symmetry condition of the Lie-Backlund. The only thing that changes is how we define the base manifold, the transformation of the base manifold. It follows from the above definition that the Lie-Backlund symmetry preserves a set of solutions U of the differential equations if xu equal cu, where c is a constant. A special class of Lie-Backlund symmetries are the contact symmetries. Contact symmetry is a Lie-Backlund symmetry where the generator depends only on the first derivatives of U. The generator transformation has the following form. So if this transformation depends only on the first derivative, then this transformation is called contact symmetry. Now, an important characteristic for the symmetries of the PDEs is that if we have a point transformation or a general generator, the generator X bar defined by this is the canonical form of this generic operator. And by using this, for instance, the operator D is always a Lie-Backlund symmetry. The trivial ones is Di, is the canonical form is this one. So if we apply the other derivative as a canonical, in its canonical form, we find the D bar, then we find that the D bar is the trivial one, the 0. Hence, every function Di is also a Lie-Backlund symmetry. Now, if x equals c plus eta theta u is a Lie-Backlund symmetry, then the generator, which is a canonical form of the symmetry vector x, is also a Lie-Backlund symmetry. Since fk is an arbitrary function, we set fk to be ck and obtain c bar equals this. So regarding the higher order symmetries, the Lie-Backlund symmetries, we can transform without any problem. We can simplify the transformation and eliminate xc and actually have only the transformation in the canonical form in form of A. So in this case, we reduce the problem of the number of dependent variables. So it means that we can always absorb the term inside the eta and have the final result is the generator of the Lie-Backlund symmetry. So that is a nice observation in the case of PDEs. Since we have this point symmetry, we can write it in terms of canonical form in this form, which is a Lie-Backlund symmetry of first order. So this property holds only for PDEs and not for ODEs. This means that Lie point symmetries are equivalent to contact symmetries that are linear in the first derivative and hold only for PDs. And for example, the Lie symmetry vector, this one, of a PD is equivalent to the Lie-Buckland symmetry x bar minus ux theta theta u. So as you can see, the transformation theta theta x, the translation symmetry on the theta x, is equivalent with the Lie-Buckland symmetry on the theta u direction. So since every symmetry transforms a solution to another solution, and by definition x bar u equal a constant a u u, then here we can define by using this operator. So this operators is the one that we apply to solve, to determine the constraint in order to consider the Lie symmetry vectors to solve the differential equation. So what we will do is that we will define the Lie point symmetries, and for the Lie point symmetries, we define the canonical form, which is of this form, and this canonical form give us the later constraint. Now, in the case of PDEs, which arise from a variational principle, Noether's theorem is extended as in the case of ODEs. So for second order PDEs, for simplicity, I consider that case, since and the Lagrangian is this one, Noether's theorem is extended instantly as in the case of ODEs without any difference. However, in this case now, in the case of for PDEs, we don't have a conservation law, we have a conservation flaw. This is a conservation flaw, and this is not a constant. This satisfies this condition. When this is ODE, then this is reduced to a constant number. Okay. Let us see now some applications, some simple applications. And let us assume a system, a nonlinear system of PDEs, known as GenQS system. This is an integrable system with smooth multi-soliton solutions and well-known and well-studied in the literature. So we shall investigate the Lie point symmetries for this system. Now, we apply this theory. I omit the calculations, and the GenQS system, we found that it means this set of 6 symmetry vectors. I haven't presented anything in group theory. I assume that you know the basic definition of group theory, the basic element. So we remark that the 6-dimensional Lie algebra, G6, is composed by 2 3-dimensional subalgebras. These are observations that we are doing, which are necessary to do the reduction and understand how the symmetries follow when we reduce a symmetry. And as I explained in the previous mini course, in the previous lectures, this is an essential in order to understand the group properties of the differential equation. So the non-zero commutators of the admitted Lie algebra are this one, and from these we define the subalgebras and the definitions, which is A38 and A1, semi-direct A1 in the Patira-Etiol classification. So these are the commutators in a tabular way. As you can see, the table is disymmetric, as expected, as the definition. Now, each symmetry vector, for each symmetry vector, we can define the invariants which correspond to its case. So for these equations, for the 6 symmetry vectors and for all the elements of the one-dimensional optimal algebra, I present you the invariants we can use to reduce the equation. For instance, for the symmetry x1, which is x1 is a translation, is a symmetry where we have a translation in time. The invariance is the x, the u, and the v. For x3 is the x, the t, u, v, etc. And this moves on. And these are all the invariants that we can construct from the Lie symmetries. So these can be used to reduce the equation and simplify it. Let's go to another second example. Not to demonstrate the novelty of the Lie symmetries, we will proceed with the application of the Lie variance to the derivation of closed form solutions. So let us assume now that we apply the invariance of the symmetry vector x1. So x1, the invariants are these, x, u, and v. So we consider that u and v are the new dependent variables and x to be the new independent variables. So by replacing, assuming that u and v is independent in time, then the original equation is reduced to that system. This system now admits the following point symmetries. We calculate it because we can apply the symmetry analysis to reduce it further, to continue. So this system admits the point symmetries x2, x5, and 6. So the symmetries are this one. As you can see, these are new symmetries, which are not symmetries for the original system. The original system admits 6 symmetries, but now we have 1, 2, 3, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 new symmetries. These 2 new symmetries are known as type 2 symmetries, and actually are non-local symmetries for the original equation. Now, we observe that this system now is maximum symmetric. It has this property, which means that there exists a transformation where the system can be linearized. And indeed, if we consider the change of variables, the dynamical system takes this form. And the analytical solution is expressed as follows. So this is a generic static solution for the original equation. As you can see, by applying, we consider that the system is static, the solution is static. This corresponds to the application of the solution to be invariant to x1, to the time translation. It means it should be static. Then the reduced system, we found from the symmetry analysis that it is maximally symmetric. Then the symmetry analysis, we found this transformation. And from this transformation, we found a linear system of ODEs, and we solved it easy peasy, and we found a general static solution. Now, if we wanted to apply the stationary solution, then U to be ut and V to be Vt, the stationary solution follows as a result of the similarity transformation provided by the vector field x2. The reduced system is nothing else ut Vt, and the stationary solution gave us that U and V should be constant. Now, on the symmetry vector x3, let's go show the vector x3 and see the invariant. So on the vector field x3, the invariants are x, tu, v. So we assume that x is the new independent variable, t, u, and v, these two set to be the new dependent variable. So by applying this change variable, now u capital and v x to be the new dependent variables. By applying these change variables, we find the system 23, 24. This system admits this point symmetries, 1, 2, 3, 4 symmetries, and this, the u, theta u mean minus v, theta v, it's a type 2 symmetry. For function ux, it follows we can find easily this is generic solution. We substitute before in the 24, we solve, and we can find the solution of v to be iota 0 integration constant over ux. Thus, the closed form solution is this one. The vector field x5 provides a similar transformation u, this solution with this transformation, which is actually always a solution of the original system. That's a nice observation. Now, from the vector field x1 plus beta x2, we find the similar transformation u, v, which is this one, and the reduced system is this one. This system admits the least symmetries vectors, theta x and theta u, this rotation. And by using these symmetry vectors, we were able to construct the closed form solution of this one. And of course, in a similar way, we proceed with the rest of the symmetry vectors. So we stop our discussion here. Now, is any comment? Do you have any comment? And I will really appreciate if you have. Okay. Since you don't have any comment, I will continue now with a problem known as group classification problem. The group classification problem was introduced by Andronikos in the 60s, where he performed the classification where he determined all. Okay, I have a question. Okay. So Andronikos considered this nonlinear now PD, and he found all the possible functions FU, forms of FU, where these equation admits symmetries. And admits different algebras of these symmetries. So, for instance, when this is a constant, the view is a constant, then this is a heat equation and we present the symmetry before. But if it's another function, maybe there are maybe less symmetries in this case. Or more, I mean, depends on the properties of time. So, but the maximal symmetric case is that it would be a constant. Now, consider the 2 + 1 quantum Zakharov-Kuznetsov equation, where fu is an arbitrary function, and function fu will be determined by the group properties of the differential equation. So we will use the least symmetries conditions to determine fu such that to find as many solutions as we can. So indeed, when fu is linear, the admitted least symmetries are this one. When it's power law, the admitted least symmetries are 5. Before we had 5, now we have these. When fu is, sorry, I had a mistake here. This should be a constant, not this should be a constant without the uni. So when C it's this one, we have these symmetries. When D is this one, F is this form, we have these symmetries. When it's exponential, we have these symmetries. When fu is logarithmic, we have these symmetries. And for arbitrary fu, the admittedly symmetries are just 3. So as you can see, the form of the symmetry vectors is different in each case, and the number of symmetries. So, and its symmetry, its set of vector fields, that means a different form, a different group. So there's no transformation that relates the different algebras, the different equations. However, all of them, as you can see, possesses a common set of symmetries, which is the x1, x2, x3. Some function of u has a 4 symmetry, while 2 functions, what we found before, the linear and the constant, remove these to be constant, remove the u me to be 0, sorry, the me to be 0. So this is a maximally symmetric case as the 2 case above. Now, if we assume now the 2 + 1 Q-Zk equation with time varying coefficient defined as this, the time varying 2 + 1 Q-Zk equation, for which without loss of general we can assume delta t to be equal to 1. We can do that by divide by delta and change the time. For arbitrary functions lambda and eta t, equation 31 admits a 3-dimensional Lie algebra comprising the symmetry vectors x1, x2, x4. However, when bt are parallel, there exists the additional symmetry, while when bt is exponential and ct exponential, the additional symmetry is this one. So this is an additional symmetry, but it has a different algebra with the vector fields before. Now, I will present you a recent application we did for the study of the SOMS equations fluid dynamics and the Cargo-Leroux models. Is a system of 1 + 1 hyperbolic partial differential equation expressed in this form, where Qx and Qt are constrained by this. For the fluid, we assume a question state parameter of a Chaplin's gas. This is a generalized Chaplin's gas. Actually, the Chaplin's gas is revolving when gamma equals 0. Now, for gamma equals 0, the latest system admits a 6-dimensional Lie algebra, which forms this form, and 6,4 is a so these vector fields. We can see that the x1, x2, and x3 are the translation symmetries of the planes, 2-dimensional plane. x4 is actually the Galilean boost, and x5 and 6 are the scaling symmetries. These vector fields form the A4.6 symmetry A21 Lie algebra and the Patera classification scheme. However, we can see that when gamma is not 0, the admittedly symmetries remain 6, but they form different Lie algebra. Specifically, the vector x5 is modified, is replaced by this x5. So this replacement provides us with a different algebra. Now we go to introduce the Lagrange variable ft and fs, so we can write the Cargo-Leroux system in the form of just one PDE in the Lagrange variables of equation 36, we observe that the Lagrangian, that the function 36, equation 36 follows from the variation principle of the Lagrangian 37, where for gamma non-zero, for gamma different than 0, different than 1, sorry, while for gamma equal 1, the corresponding Lagrangian reads for gamma equal 0, sorry. Now, for gamma equals 0, the action of the point transformation, which tests the symmetries of the equations in the Laplace equation, in the Lagrange variables, are this one. So y1, y2, y5 are related with the homogeneity of the background space, where ST now are the differential equation, where equation lies. Furthermore, y3 is related to the momentum, and y4 to the Galilean transformation. Finally, the y6 is a scaling symmetry which states the existence of singular solutions for the differential equation. For gamma non-zero, the previous symmetries exist, the same algebra exists, where now the y5 and y6 are replaced by these two expression forms, and they form a different algebra. But not only these symmetries are Noether symmetries, but we found for the first case that this 1, 2, 3, 4, and this one, the combination of y6 and y5, is also a variational symmetry, another symmetry. So the corresponding conservation laws, I just presented the first ones, are this one. I don't present this one because really not necessary, but you can calculate this. So conservation laws relate to the vector y1 and y2 define the energy for the stationary static solutions, while the conservation laws relate to the vector field y3 and y4 are the momentum and the Galilean transformation. We do the analogous with the analytic mechanics. So for gamma different than 0, these are the conservation laws. This for the first vector fields, and only the vector, here we have only the vector fields y1, y2, y3, and y4 are symmetries, while the rest are not symmetries. Now, if we want to apply the symmetries to find the reduction, find the solution, so we consider the y1, the linear combination y1 plus ay2. This give us a solution which is a travel wave in the Lagrange variables. The reduced equation is this one, and the closed form solution is this one. So it's going out, but it was a very long expression. You can easily solve equations 47 by hand. Now, this equation 47, follows from the variation principle, and this is a Lagrangian actually, of 47. Hence, this Lagrangian means Noether symmetries, and the Noetherian conservation laws are this one. So by applying again the symmetry vector, the symmetry analysis, we were able to find conservation laws, and this one leads to the original solution for the original variables is this one. So as you can see, we're able to construct the solution, the original variables by constructing the Lie symmetries and the Noether symmetries in the Lagrange variables. Now we assume the y6, y2 leads to the similarity transformation, and this transformation leads to that equation. And this equation, as you can see, is similar with this one. It's also not different, a small one, but an equivalent, the later transformation is expressed in this symmetry form, and the solution is given by the Lambert W function like that. Now we assume the symmetry vector, we apply this transformation, then we ended with a linear differential equation, and this is the solution. This means this equation follows from the Lagrangian, which is maximal symmetric, and is 5 Lie symmetries and 5 conservation laws, and easily the analytical solution, the original variables, is this one. The similar transformation related to y6 and ay is given by this expression. The reduced equation reads, and we write it in, we can express it easily and recover everything as before. So that was, I want to demonstrate you the application easily to understand how the symmetry analysis can be applied to solve nonlinear PDEs and ODEs. So I will show you an application and how we use the symmetries as a geometric criterion in dark energy. So I'm working in cosmology, and in cosmology we have a set of what we solve of the Einstein field equations. The Einstein field equations are nonlinear differential equations. So I just show you the basic definitions. I mean, it's not part of this course to explain you this one, but what we solve is the Einstein field equation, and we solve this set of fluid dynamics. So as dark energy is characterized the matter source which drive the cosmic expansion, the unknown nature of that matter source is a puzzle for modern cosmology. And there are two possible ways to solve the problem. Introduce an exotic matter source in GR, scalar fields etc., and modify Einstein's general relativity, modified alternative theories of gravity. The cosmological constant can be seen either as an exotic matter source or a simplest modification of the Einstein-Hilbert axiom integral. The main idea of the modified theories of gravity (MTG) is the variation of the new action integral. So we modified Einstein theories of gravity such that we introduce new geometric dynamical degrees of freedom in general in the theory of gravity. So I don't want to focus that, and I will present you a model that will apply the symmetry analysis to study it. This is called the Brownsdick theory. The Brownsdick theory is a theory of a scalar field, which is the scalar field is minimally integrable to gravity. So in cosmological case, the field equations are this one. And if we go in the cosmological case, these are the set of differential equations that we have to solve. So this model has a three parameters, a three function, B3. And what we will do is that we will apply the symmetry analysis to determine the function Wi-Fi. So the field equations for admits Lagrange, Lagrange formulation. They follow from this Lagrangian function. And we shall apply Noether's theorem condition to classify the Wi-Fi as defined by Ovsyannikov as we did before. So we apply the symmetry analysis. So we have a dynamic, recognize this, we observe this Lagrangian, and we observe that we have a dynamical system of 2 degrees of freedom. The Lagrangian describes the evolution of a particle in the two-dimensional manifold in the variables A and phi under the action of a potential, of an effective potential. The dynamical system is autonomous and admits the conservation loss of energy. The existence of the constraint equation tells us that the solution holds for the specific value of the energy, which means that evolves for specific volume in the phase space. That is a very important characteristic. There is a constraint that the energy is zero. Parallel solutions or exponential solutions describe specific points or the time phase of the universe, but are special solutions. The numerical solution is accessible in initial condition, and it's unknown if a real solution of the problem is described. We need another conservation laws to prove the integrability, the existence of actual solutions for the problem. So this one has one conservation law. We can see easily. It's the conservation law of energy. It's an autonomous, and due to the field equation, this is zero. So we shall define the B-phi such this model to admit additional conservation law. So this second form of transformation it's not necessary to discuss about this. The symmetries remain valid in the conformal transformation, but let us go to the application. So we perform the following coordinate transformation, and the point like Lagrangian is this one. We simplify it, and we can see that it's like we have a particle moving in polar coordinates. The dimension of the minus superspace is 2. The Ritz scalar of the minus superspace vanishes. The minus superspace is a flat space and maximum symmetry. The point like Lagrangian describes the evolution of a particle in the two-dimensional flat space of Lorentzian signature. For specific function with theta, Newtonian analogs will follow. So we solve the symmetry conditions, and we solve them, and we determine all the functions with theta, by phi. As you can see, theta is related to phi like this. where point symmetries exist, and these conservation laws, we will use them to reduce and find solutions for the original system. So, as you can see, there are different functions, 1, 2, and this one. We have this one, which are more general from the previous one. As you can see, there are different vector fields, while there are similar algebras, but the vector fields are defined differently. It depends on the functional form of the case here. And of course, the case where the scalar field is free, it's maximum symmetric. Now, we define a new coordinate set. We can easily determine these coordinates from the form of the symmetry vectors by calculating the canonical form. And in this new coordinate, the field equations are described by this Lagrangian function. And for each potential that we have, a Lagrangian function, the potential takes this nice form. As you can see, the first one is very easy. And for the first potential, the solution is nothing else than the oscillator. And that was really a very nice observation, since we are able to recover Newtonian analogs in the study of Einstein field equations. Now, but can we learn anything new from the application of the symmetries in cosmology? And the answer is yes. We can extract many information. For instance, consider this Lagrangian. I mean, let me go before show you this Lagrangian we had here. So as you can see, we have a Lagrangian of this form, x dot y dot. But let's now we start from a diagonal. The Lagrangian describes the two-dimensional oscillator in a flat space with Lorentzian symmetry. So oscillator, we don't have only, that means linear forces. It's straightforward to see that means 8 nether point symmetries. Also, the dynamical system which Lagrange 5 describes is varied under the following discrete transformation. So we change x with minus x and y to minus y, then the Lagrange is the same, and the complex one, everything will be the same. While under the transformation x, y, y, z, x, the new Lagrangian is L bar equal minus L. So nothing changed with this transformation. However, while the field equations have same design, the Hamiltonian constraint change. If the latter is 0, then everything is invariant. These discrete symmetries follow directly from the existence of the Noether symmetry vectors, this one. Now, consider now we have the coordinate transformation and go from the diagonal to non-diagonal variables. The discrete transformation we established before, the x minus x, y minus y, in the new coordinates is u minus u, v minus v, while the transformation x minus x corresponds to u minus v, and y equal minus y corresponds to the discrete transformation u, v, v, u. All these transformations are related with the admitted translation group of the flat space. In the new coordinates, Lagrangian takes this form. We assume now the second coordinate transformation from uv to AV, and from 67 we reach it to 69, where p, q are constants on omega. I don't have them here, but these are just constants, and assume that omega has this form. In the new coordinates, this Lagrangian, 67, takes this form. And this is nothing else than Lagrangian of the Brand-Fix scalar field for a potential, for this potential. The latter Lagrangian has the form of the dilaton field with a difference in the coefficient of phi dot. Furthermore, it's easy to see that under the transformation phi, the Lagrangian 69 becomes a Brand-Fix explicitly, as we had it before. From transformation 68, if we take this discrete transformation y to minus y in the Cartesian coordinates u, v, vu in the coordinates uv, this actually reads as the following transformation: a, it's equal a bar, a minus 1, if and only if p plus equal minus p minus. This constraint, this equation, gives us a specific value for the free parameter omega that we have here. From where we find that there exists only a unique solution when omega equal 1 or omega plus equal 1, where 69 corresponds to Lagrange of the dilaton field. For this transformation, actually, it's what we call a duality transformation, and it means that the scale factor duality, if we're saying this solution for the scale factor, and we inverse the scale factor, then the equations and the Lagrangian remain the same. So there is a discrete symmetry which we are able to construct. Why this is important in terms of physics? This is important in terms of physics because for this dilaton field, for this specific Browns-Higgs model, if we know the solution in the present time, then by doing this change of variables, a equal a minus 1, then we know the solution in the past. So if we assume that a is large, then we know the solution in the very beginning of the universe. I mean, in the very early stages, in the ball, in the area next to the Big Bang. So this transformation, it's not only while the a equal a minus 1, it exists only for the omega equal 0, omega equal 4, but these transformations can be generalized for other models and it can be extended in this form. So we can construct new solutions from new solutions by using the symmetries of differential equations. I want to thank you a lot. I'm free to questions. And before I proceed with the following 5 minutes. So is there any question that you have? Okay. If you don't have any question, I don't see. Okay. So another nice thing that we can see is like, okay, can we use AI these days? I mean, we are in the ball of AI. So can we use AI to study the symmetries of differential equation? So I created ChatGPT. I created ChatGPT. And to do that, to do the symmetry analysis, and let me try to use it. Okay. So let me say that to you. I can say that the ChatGPT that I created still I train it, but you can ask me if you want. So if I open the correct ChatGPT, is this one? So I call it a symmetry analysis, and you can ask it anything you want. And I will tell you that until now works well. For simple model problems, does not create. It's correct, but for more complicated equations, you should verify it. Doesn't work always well, and it's still training. So, but it's a nice way to have a learning curve to understand the procedure and how it works. So, for instance, I want calculate the symmetries of the differential equation. Let us calculate the symmetries of this differential equation. So we ask it if you okay. The list and the answer that give us actually it's correct. Define the D, write in this form, set up the symmetry generator. We have considered we have point symmetries. Find the prolongation, apply the symmetry condition, determine the prolongation, find the variant condition, this is a symmetry condition. Shortcut for this equation. And okay, this is presented as a variance condition that I will ask for that, but gave us a symmetry vector, which is correct. This is the SL2R algebra, this is the Markov equation. But now, I mean, it has suggests us how to apply the symmetries. And let me ask it, please print, don't ask please, because it's expensive, please print variance. Let us see. I should train better, but I will be happy if you can do it for me. Okay, let's find step by step. Let us now work. Okay, let's go to the second of the PD. Okay, I will dissipation. I hope that the change of notation is not a big problem with what I presented, because I trained with another book. So as you can see, defines the Coulomb coefficients, everything, and now we'll apply the variance conditions. Okay, and these are the symmetry vectors that I presented before. Okay, let me see if we can do a reduction. Can you apply uh, 7 to reduce the equation? We'll now reduce the PD. Okay, it's kind of symmetry. Find the invariance. It's going well. We solve the characteristic. This is a way to find the variant. It's not the unique way, but it's one of the ways. Do it. Very nice. Exactly, and reduce it to OD, this OD, and that is the solution. So any solution is for. So compute the derivatives. Okay, it's doing step by step, so you can learn to do it. And replacing, you end it. Okay, let's apply the chain rule again. And do it very analytically. Okay, replace with OD and to the PD and end it with that OD. Oh, it made a mistake. As you can see, you should not trust it always better, well, because as you can see, it made a mistake. It's not the first time that ChatGPT makes mistakes, not only of this, but in general. So now, yes, doing correct. Ah, that is interesting. I didn't try this. Now I did it correct. This is the correct definition. And if you do it by hand, you will find this. This is the reduction. So as you can see, ChatGPT as it is, can help us until a point. But as you showed in this example, it's not necessarily 100% correct. So if you need that trained ChatGPT, please mail me. You have my mail. You can find my email, so I will be happy to share it with you so we can train it further. So do you have any question, please raise your hand or open your mic. I'm happy to answer any question. Okay. I want to thank you for being here, and maybe I will see you in the future, hopefully. Have a nice day. Be well and enjoy your studies.
Thanks, same to you.
Bye.